Welcome. I want to first introduce STAMP and STPA. Y'all may not be very familiar with the acronym, and the acronym is presented here. Of course, you know PHA, Process Hazards Analysis. The ST is Systems Theoretic. The A is Accident, M is Model, and P is Processes. So it's kind of a unwieldy acronym, STAMP. STPA you could think of as STPHA. It's the Systems Theoretic Process Hazards Analysis. That's the tool that's used to implement STAMP. STAMP is the model, the accident model. STPA is the tool used to implement STAMP. So again, ST, Systems Theoretic. So it's a systems-based model. You can see right off the bat by the lingo there. STPA, they could have called STPHA, Systems Theoretic Process Hazards Analysis, and that's what we're here to talk about today. Now, I'm assuming you all have a good background in PHA and what it is and the different methods that we have. HAZOP, we have what-if studies, we have FMEAs, we have CHAZOPs, and so I'll be making a comparison in a little bit. That's our context of comparison is with the tools we have in PHA, and we'll be discussing how do they compare and what is different about STPA specifically, that tool, and how can it augment our skill set in our toolbox. That'll be part of this talk. But first, to start with, STAMP and STPA have gone viral, quote unquote. There's a lot of buzz generated of the methodologies. Specifically, I'm referring to LinkedIn, and there's just a lot of interest in the methodology. There's a lot of claims being made, and so that was part of the motivation of why I'm also looking at this, is to try to understand it a little bit better. I do want to say up front that the accident model STAMP and STPA are both in the public domain. They belong to Professor Nancy Leveson from MIT. The credit really does go to her. She has created over the past 20 years, really. She started in the 2000s creating this model. She published a book on it in 2012, and since then there have been what are called extensions to STAMP that have come out. I'll have a slide on the extensions or the application specific domains of STAMP, but the credit really goes to her for creating this, and it has gone viral. There are industries all over the world using it now: automotive, airline, healthcare, military applications. The one application maybe that hasn't caught on so much yet is, interestingly enough, process safety. That hasn't. It has within our domain, within process safety, and so we'll look at maybe why that is when we do some of the comparisons here. But I did want to mention that these are public domain. This is a public domain model. Comes out of MIT. Professor Leveson, who I'm sure you guys know, she's a longtime safety practitioner, has done a lot for the advancement of safety in general. But MIT holds a workshop every year. They freely post the presentations, the YouTube videos of the workshops, all the discussions. So all this is discoverable if you have interest in it outside of this brief presentation I'm going to give today, this brief webinar. Please check it out, because it is there, and you can make the determinations yourself how you can use it. Should I use it? That kind of thing. I can give you an introduction to it. It won't replace PHA. Our tool set, as I mentioned, HAZOP, what-if studies, FMEA. I mean, it's not going to replace that. I'll kind of talk about a little bit why that may be. But it does have a niche, and it does look at things a little differently than we do in our HAZOP studies. Say it takes a different viewpoint, and that's the STAMP model. It is a systems model, and so I think it does look at things a little better way than maybe what we're doing right now. That we could be using it. That's going to be my position. Okay, so let's go ahead and get started. The context for the talk also came out of GCPS 2022 that was held in San Antonio last spring, Global Congress on Process Safety, which was part of AICG Spring Meeting umbrella. That's why the next couple of slides are going to talk about transient states of operation. I presented this paper, like I said, last month in San Antonio for GCPS. The track was identifying hazard states for transient operating modes, and so I was giving an introduction to the audience there about what I consider to be transient operating states. This is just how I break them down. It's not so much relevant for the presentation for you guys on the webinar, although I will have some specific examples of the STPA analysis later on that deal with what I call transient mode. Here's some examples of non-routine, abnormal, or maintenance tasks that I've looked at specifically in my work over the past number of years, doing analysis on qualitative analysis, quantitative analysis, and how I think the STPA PHA method can augment these and really can be used a way to implement these kinds of studies that sometimes get triggered. And I'll talk about a work process and how that might happen. Okay, so I wanted to set that framework of how the transient states come into play, and that's how it came into play. That was the context of the paper for GCPS. All right, so let's continue on here. Now let's first look at similarities between PHA, our PHA methods and STPA. Again, systems theoretic process hazards analysis. These are all hazard analysis methodologies. They use the structured parameter plus guide word / question concept. Okay, very similar to what we do. All can be captured on a cost consequence worksheet. All generate recommendations to improve safety. They're performed with the facilitated team. They involve the same level of effort, all things being equal. One of the other claims of STPA and STAMP was it would be faster, it's less costly, and it does a better job. And I think some of the claims that you'll see if you do some research and some background, you go back a couple of years, I think those have kind of been backed off a little bit. Really, there's no free lunch in process safety. And in fact, it's worse than that. It takes a lot of effort to implement process safety as a preventative means, you know, and I'm talking about not being reactive after something bad has happened, but really trying to prevent things is an enormous amount of effort. STPA, the level of effort that you would use to implement it is the exact same thing. There's really no savings there. I'll make another comment on that in a later slide. All are highly dependent on the makeup of the team and the dynamics of the team. The tool is only as good as the team. The tool is only as good as the facilitator. The tool is only as good as the quality, the competence of the team that you have together when you're doing an STPA study. But you can see from this slide, they have a similar feel. You can read down through here. It almost feels very much like HAZOP. Now I'm going to have a slide on the differences and point those out as well. But there are similarities, and so it does provide that kind of common feel. Now some differences here. The first one's interesting. It could be an entire presentation on its own. STPA and STAMP, and even Professor Leveson. And she even has used this claim, or his words. It's more of a religious argument, quote unquote. So it's a little bit funny, but it's not a risk-based method. And so I don't want us to get tripped up on that as process safety people. We use risk-based tools that consider consequence and we consider likelihoods. The STPA tool does not have any outreach or any way to roll in likelihood in terms of probability or frequencies. And it's just not part of the method. It is a hazard-based method. It's not a risk-based method. So if you want to apply probability or likelihood on top of STPA, then you would do that outside of the STPA tool. That's how I've used it. There are very religious arguments about why, considering future events where we don't have any predictive ability and the validity of using these probabilistic methods. I mean, those are more philosophical arguments. I don't want us to get tripped up on that. And please, when you see that, when you start to look at this, don't let that keep you from let that argument keep you from the methodology. That's just something completely separate and worthy of its own discussion to have. That's the first one there. It is the other thing that's a little different about STPA than PHA is it's a top-down approach, so it kind of works backwards. You start with the consequence, and then you work toward the causes. HAZOP could be more, you work for the causes and you go to the consequences. So, but that's even minor. If you're an experienced PHA person, you know that sometimes you start with the consequences, sometimes you start with causes as you're documenting hazards on a worksheet, and that's really a minor thing as well. The one big thing that you'll notice is STPA uses one parameter, which is control, and two guide words, not provided and provided in the wrong way. And so the idea is you're trying to identify unsafe control actions, and we'll talk a little bit about why control. Okay, it's the methodology itself comes, and the STAMP methodology is a controls-based methodology. Okay, and that's kind of where it comes from. I have a slide on that, but you can see here, you're like, well, that doesn't look very impressive. It's got one parameter. What about flow? What about pressure? What about level? What about the 24 parameters that we may have listed in a HAZOP node and all the guide words that go with those. So it does really have just this one parameter and two guide words. Now we can get a lot of mileage from that, and I'll show you some examples of that and how that's done. But that's a difference. Another big difference here. So let me highlight these couple here. So this is a significant difference. This is significant here. It uses what's called a control structure drawing of the system under analysis. So we're used to maybe P&ID, having some other types of documentation in the room. Primarily the P&ID is our founding go-to document for HAZOP and PHA, and STPA uses what's called a control drawing. You can call it a functional control drawing, a structural control drawing. I'll have some examples of what they may look like, and there's plenty of examples out there what this might look like. But that's a significant difference from PHA, how we're used to it. As I mentioned earlier, under the parameter discussion above, the idea is to identify unsafe control actions. As a part, focusing and using the control drawing, and between functions on the control drawing, functions or devices, and where the constraints of the system may be violated, the safety constraints may be violated. So this language may sound a little bit unfamiliar, but we do the exact same thing in PHA. Have we exceeded design pressure? Have we exceeded flow rate? So it's the same concept. Have we violated safety constraints that the controller has placed on the process? So it's very, very similar, although the lingo may be a little different. And then the third column over here, I'll just circle. I think actually the most value comes out of the ability to incorporate better human factors, a human factors perspective, including cognitive aspects of human factors. There's a specific extension of it of the STPA for that. This, in terms of the system boundary, you're not limited to a P&ID. You can draw, and it is a custom drawing. That's one of the differences. But you can draw a control structure, include whatever you want in your system, in your universe to be studied. That's a big plus. That's a concept we aren't using in PHA. It does a very good job at evaluating how hazards and losses can arise, and so the causal scenarios that are developed in STPA are generally what you could call richer causal scenarios. You're going to look at proximal effects. You're going to look at conditional effects, and then also systemic effects. I'll talk about this more in a later slide, but you're looking at different layers beyond just my control loop failed or it was a human error. You're looking behind that and understanding how those conditions can arise that creates that error, that opportunity for error, makes it more likely. that's another difference about STPA. Okay, let's continue on here. So I mentioned the extensions. This is one of the reasons that the methodology has gone viral, is because people have started using STPA and they've created extensions. So you can see here some examples. I'm going to have a few brief slides on engineering for humans extension, in the engineering for humans as the controller. That's something we face in process safety. I don't have a literal hardware, controller, safety PLC, PID controller, DCS, but my human is the controller now. How do I handle that? Well, there's an extension that was created for it by one of Professor Leveson's, engineering students doing a master's degree, has published a thesis on this. But you can see here the different extensions that have come up and why it's so popular. I had a colleague mention, as I was preparing for this paper, another nice application would be, a safety critical program management for a critical project, and how you manage suppliers, and you manage contractors, and you manage constructions and installers, and that would be a great application for STPA. And there's another extension right there. Okay, let us move on. The one question we can ask, aren't current, before we get too deep into STPA, let's just take a pause and say, aren't current PHA methods adequate for evaluating, the hazards of the process, including transient mode? Well, there's a couple of things here. For both PHA and LOPA, they normally stop at human error as a cause. Human error is recognized as a consequence. It's not a cause, it's a consequence of the system. It could be the system design, it could be design-induced error, it could be maintenance-induced error. So we really limit ourselves when, especially for high hazards that have a significant human component, and we don't look beyond just the simple human error. I mean, we may wait till something really bad happens, then we spare no expense to ad nauseum detail out what the way to fix this. We need to start doing that before these things are happening. We're not definitely diving deep enough right now into human factors, human error, human reliability. We're just not. I have another slide on that. Okay, hesitation to document or even consider control of work scenarios, not in scope, maintenance scenarios. I just was in a PHA where, we have that covered. We're confident our site does this well. These types of scenarios around preparation for maintenance and ensuring that proper isolation is made, and equipment's depressured and cleaned out before things are opened up, and the likelihood of even being on the wrong equipment. We're gonna, you just a lot of hesitation not to spend time documenting these. Not in every case, but in some cases you see that. There could be a bias to downrank human-centric scenarios to keep out of LOPA or claim they're not LOPA, which they aren't. LOPA is not the proper place to do a scenario that has a heavy human factors component, human administrative controls, human error. It's really not LOPable. You hear the claim sometimes, this one here, we don't take credit for humans in LOPA. You definitely are implicitly. I think what people mean by that, for example, we don't take alarm credit, so we're not taking a human response credit. Well, beyond the fact that your LOPA is entirely a human endeavor, you are taking credit for humans. They're baked in either to a cause, an initiating event. They're baked into the maintenance you're performing on your hardware functions. There are so many ways the operations interface with that hardware barrier. Your humans are there. When you say we don't take credit for humans, and I hear people high up in process safety making this claim, and it's a very ignorant claim. I'm not saying it's a stupid claim. I'm saying it's ignorant, and it's not correct to say that. You're missing something really big if you just claim our LOPA doesn't take credit for humans. There's a huge chunk you're missing there. Some people try to handle this by checklists. We cover human factors in checklists, and it's just like anything else you try to engineer by checklist. It cannot be done. There's always going to be something not on the checklist that you needed to look at. So it's not a valid way to do it. And then, as I mentioned, the level of detail from causal scenarios is really missing from our PHA. They're too simplistic, and they don't really describe how accidents can occur and how they can arise. Okay, let's move on. I said I was going to present a brief work process, and the funny thing is, talking about GCPS this spring, um, every presentation, every paper I heard dealt with and asking us to do more. That what we're doing right now is not sufficient, and it doesn't take a lot of insight. You can see the accidents are still happening all over. They are still occurring, and so I just found it very interesting. Every paper I sat in asked us to be doing something more than what we're doing today, and that costs money. That's the bottom line. And I made the comment earlier, process safety, there's no free lunch in process safety. In fact, it's much worse than that. It's very expensive. And so I'm doing the same thing. I'm asking you to do more. This is this STPA, the way that you'll run STPA and the STPA study, and maybe the extension engineer of humans is to cull out of your PHA these kinds of tasks that are human centric. They have a large human element. You may say you can even pare them down from there. You might have a high degree of uncertainty about the task. It may be a high hazard, right? You're going to do more filtering, but I'm asking you to do something more, unfortunately. In addition to PHA, I know that's not a popular opinion. In fact, at the GCPS, it's such an unpopular opinion. There was a PHA method for drift, for that concept of drift, and and a big part of that was how you would do this. And to save money, you would not do your reval PHA, because you could use that money now to do this this PHA based on drift, this subtle drift into maybe possible a dangerous condition, and it's just very telling that had to be a part of it, based on the fact that the money has to come from somewhere, and we all recognize yes, it's very legitimate. I wanted to say very briefly, the STAMP is the accident model. STPA is the tool again. I'll show you some examples of that, but I wanted to show briefly Leveson, how Leveson's model was influenced. And if we start here on the right side of the screen, the STAMP model is actually influenced from Rasmussen's model. You can call it migration toward the boundary. And one thing that's interesting is we should always ask the question, what accident model are we using in process safety? And we could say, well, maybe the Swiss cheese model, and we kind of do that, I think, in a way. Our LOPA is sort of the Swiss cheese model, although Professor Reason's development of it included a lot more than just what we might put in a LOPA. But this is interesting because not only did it influence the STAMP model, but you can see here, as I write here, the hole in the Swiss cheese is kind of this right here. We have economic pressures. I was just talking about economic pressures. We have human pressures, and as these expand that boundary, as we expand the margin out toward the boundary between unsafe and safe, the holes in the Swiss cheese get bigger. So I just thought it was an interesting way to look at it. Here's safety down here. We're pushing back, but the problem is we're constrained by the same economics. And so maybe really this is a futile end game, and we're just baked into the same economic system, and we're going to be ultimately limited about what we can achieve and what we can do, because we're, like I said, we're baked into that same pie. Unfortunately, we don't reside outside of it. But I wanted to show you that. Now, there's two things here. Systems theory, go big. You're gonna expand the boundary that you're gonna run your study on, through the control diagram. You're gonna bring in things just more than a P&ID. And then the ability to go deep, the causal scenario. So you're going to be able to step from proximal causes. That's the operator. The proximal cause is the frontline operator turning the valve, pushing the button. Two conditions, that's design-induced error, maintenance-induced error, operations-induced error, to even higher level systemic factors. I'll have some examples of those. The idea might be to attach SPI, safety performance indicators, to the delta here. And so when you're approaching the boundary. So there's just a lot of meat here that you could really take from this model. And it did influence STAMP. So and specifically in these ways. And the idea is a normal accidents, emergence, and control theory base. These are the foundations of STAMP. You know, it doesn't take a failure to have an accident. It's a little clickbaitish, but Professor Leveson gives plenty of examples of that. The idea of emergence is it's not about the individual components, it's about the interaction between the components, and the property emerges from the interaction, a good property or a bad property. And the control theory based aspect of STAMP comes right from control theory. So you're going to have constraints, you're going to have feedback. I'll show you what that looks like here on the next slide, how it looks like a controller, a PID controller controlling a process. And so I wanted to make you aware basically of the background model for STAMP. Let's continue on. So here I'm going to have a couple slides on control structures. Again, this is what you're going to STPA your study against. This first one up here is just a generic layer of protection control drawing. You've got feeding down here, the safety constraints on this side. I've given you some examples of those. You've got the feedback here, the feedback and monitoring of all the different types of things you can do to ensure the barrier is available. And I say here that the barrier integrity is not a property of the barrier here. It resides in the interaction with the controller. And so it is kind of interesting when we consider reliability, we really focus here on our reliability. We don't focus so much here. You can't really separate them. They're a system, and that's the whole point of this. And I'll have a really good example on a barrier that is purely on the surface. It looks like a very simple mechanical barrier, but it is a 100% human barrier. Is that my next slide? That'll be my next slide. So let's get to it now. But this gives you an idea of what a control structure looks like that you would STPA against. All right. So here is a real world application. We have here a rupture disk. The emergent property that we're interested in is the rupture disk availability. Now, the funny thing is the rupture disk is about as simple of a barrier as you can get. It's a thin piece of metal. Now, I say simple. There's an entire manufacturing process that goes behind it, which is represented here. There's a stores interface. There was a finding with stores. So all of these components to the control drawing, you're not going to find these on a PID. And when the study was done, there was approximately a dozen conditional and systemic weaknesses identified. So, for example, operations role. Let me get my pen centered here. That was found that, and let me back up a minute here. So the hazard, you can see the hazards here. You may have read it. So install backwards, wrong disk, plugging, isolation valve less closed. I mean, these are the things that we're analyzing to determine the rupture disk availability. And let me take one more step back. Why was this study even done? Well, the end user of the device was trying to claim a certain amount of credit for the rupture disk to protect, and it was above and beyond what you might normally claim in a generic credit table. So that's why the study was done. Okay, if you're wondering. But the conditions, some of the conditions that were found. Operations had an opportunity to provide an extra sign-off on the installation coming out. I mentioned stores. There was a data point where stores was supplying the wrong rupture disk out to first the quality inspector. Everything went through that person. I'll talk about that role in a moment. But there was a certain error rate associated with the stores and what they were supplying out and how they had the disks stored in bins, and sometimes they would get mixed up and put in the wrong place. The manufacturer sometimes was not supplying the test reports as they should, and the MMS had some deficiencies. That one may be more obvious in terms of scheduling PMs and having everything recorded in there. But the big finding of this study was the QC inspector. You notice the QC inspector is sort of the backbone of the whole structure. Everything went through them, and so one of the opportunities to work on a disk and perform PM on these rupture disks was during turnaround, and turnaround is a 24-hour endeavor. And so what was found was this QC inspector had been at the site, had worked there for decades, they knew everybody, they knew the roles, they knew who they had to talk to, how to get things done. But during the night shift, you pulled basically in a warm body to do all that, and you really lost a very critical layer for ensuring your rupture disc integrity. So technical training. So recommendations were made around technical training for the role, authority to act, communication requirements with all the different people that had to have been talked to, controls around who is allowed to fill into the role. Those were some of the findings from this STPA study using this control drawing. So a lot of value was added because you definitely don't, you do see periodically, get my highlighter back here, you do see this. I'm sure many of you on the call have seen these things happen, and we're working to minimize that, to identify weaknesses, latent conditions before something bad happens. All right, example 1. Example 2, so this was truck unloading. There were specifically 2 chemicals that were being brought on site that could be a mixing concern in a tank. Okay, so specific chemicals were identified. They could come into two different type tanks, and the site had a lot of very good controls already. And so the control structure was drawn. The deviations were asked on the different controls that would feed down the control structure, and also feed back. So that's that part of that monitoring. The emergent property frequency of unloading the wrong truck. And this one was interesting because the weakness found here was, as you can see, drivers are not allowed to make connections. This one right here, but there was one unit buried in this very large site where the drivers did everything. They made connections and they unloaded, and it was one of the chemicals that was going to be involved in this inadvertent mixing scenario. And so it wasn't a far stretch to imagine potentially this driver coming in, expecting to make connections and unload, and getting to the wrong tank. The other part of this was they were having trucks lost. It was such a large site, they were having trucks lost frequently, almost every day. And so this was a significant, weakness identified that you definitely wouldn't find in a PHA for the individual units, because you're not taking that larger systems view. So this is another example of that systems look, that STPA type look can be valuable. Now, I want to talk about, so the control structures I've mentioned so far have been, you can call them skill-based, you can call them rule-based type procedural tasks. I want to talk more about, what's inside our mind right now. And so this is the engineering for humans extension model. This person, Ms. France, developed it under Professor Leveson, published a thesis on it. It's in the public domain. It's a very good write-up, giving a lot of good background information on the extension. And this is what we're looking at here. How do we incorporate this into a control structure? It's not easy. The next couple of slides are going to just give you a very brief feedback on how I've experienced this and what I tried to do. Mental models are beliefs. When you hear the word mental model, you think of like a Lego model or something in our minds. They're really just a set of beliefs. And I say just, I'm not trying to downplay it, but they are beliefs. And that's really what the engineering for humans extension model is trying to drill down onto, is what we believe, why we believe it, and how do we update our beliefs. And there's a lot of mileage that could be made from this. The big thing here is what's called skill-based intuition. And this comes from the work of Gary Klein and Daniel Kahneman and Amos Tversky. To some extent, they have gotten together. They do belong to different schools of cognitive thought schools, but they have gotten together into some agreement. And this is a very powerful, I think, takeaway that I've used many times in these types of studies. How much skill-based intuition does, say, a board operator have? How many years does it take to develop it related to the specific hazard you may be looking at? And so, they've identified a couple of things that must be present to develop skill-based intuition. These are the 3 big ones right here. The idea, again, is you could potentially set these safety performance indicators on that, based on literally years of experience. Say of a board operator, that could be an indicator, a leading indicator. This is addressed directly in Engineering for Humans model. Now, for some abnormal situations, there's little real world practice, and that's when you bring in the whole idea between drilling and what if scenarios, and developing that as part of a program to help improve skill-based intuition. I will say, just very interesting at GCPS, that a colleague of Gary Klein's did present. I did see that, and it is so encouraging to see. And he is working a lot in the chemical petrochemical industry in these types of concepts. So I think it is going to be coming more. So be aware of that. The other thing is, talking about beliefs. Okay. If we look at some biases here, we have confirmation bias, we have fixation. Those are the two I want to talk about. Confirmation bias is a heuristic. We're wired to confirm beliefs. We're not wired to disconfirm beliefs. So this bullet here, sorry, I keep losing my pointer. It is better to confirm correct beliefs than to try to disconfirm or disprove false beliefs. So it's easier. We're not wired to disprove. Save that for Popperian science, where your Karl Popper is, we try to disprove a theory. We can never prove a theory absolutely, because no matter how much confirmation you have, it takes one instance of falsification to destroy the theory. All right, that's the white swan problem. You can have a million observations of white swans. Your claim is all swans are white. You have a million observations of white swans. Okay, hey, my claim must be good. But it only takes one instance of a black swan to falsify that theory. And so that's all good and fine for science, but for people, we need to look at confirming beliefs. So the important thing here is, and I have this as this bullet. You make sure your operators are starting with the correct set of beliefs, and then confirm on the correct set of beliefs. So, for example, for abnormal situations, to trust alarms, even though that can be hard to do, trust that there is something wrong and work to confirm that, instead of, oh, there's nothing wrong, and working to confirm that. So starting with the correct set of beliefs, I found, is important. There's also design implications for that around situation awareness. So that's that. There's taxonomies out there that can help with this Engineering for Humans extension of STPA when you do these types of studies. So I wanted to have that slide up there. And summary. So I think we saw some ways that STPA is different than the tools that we use. PHA tools that we use is based on the STAMP accident model, which is a systems model. It allows you to go big and go deep. And it does unfortunately require additional work beyond PHA, I think, is the proper way to implement it, in my opinion. But I think it can help us. Ultimately, it can help us, become safe and prevent, and be more preventative in terms of these negative outcomes that we keep seeing. Okay. Any questions? The first one up here, please, is from Anonymous. Please, could you enter the full name of the acronym STAMP in STPA? Yes. Again, ST is Systems Theoretic. It's the same in both acronyms. AM is Accident Model. So STAMP is the accident model. STPA is stuff that prevents accidents. That's a kind of a humorous acronym, or a humorous way to explain STPA that came out of MIT. I give them credit. Stuff that prevents accidents. So that's Systems Theoretic Process Analysis. It's funny because if you look at marketing, a lot of science is dependent on marketing and engineering, and they would have done well to call that STPHA and versus just STPA. So STPA. So again, the question is, What are the acronyms STAMP and STPA? STPA, which is the tool, the hazard analysis methodology, STPA systems theoretic process analysis. I like to say STPHA. STAMP is the accident model. That's the AM for that systems theoretic accident model and processes. That's the model that that STPA is based on. It's a systems model. And I think there's another question down here that's going to talk to that a little bit as well. It says, from Anonymous, please, is the paper mentioned on transient operation states available? Yes, please contact the moderator, Jonathan Chapman, and send that request to him, and we can get you the paper. This is the paper that was presented at GCPS last month in San Antonio as part of the GCPS with aeSolutions. Yeah, please make that request through Jonathan. Next up, have there been any formal papers written comparing PHA and STPA directly? Yeah, that's a good question. There is one published case study. Again, it's on the MIT website, as I mentioned. All of this information is in the public domain. But it was written for comparing an incident that happened that a PHA did not identify a hazardous outcome that STPA caught. Okay, so it was a PHA, or it was a HAZOP methodology, and the paper was written about how if they'd done STPA, they would have caught it. Now, when you actually see it and view the material, well, and if you're a seasoned process safety person, you know that you're just as likely to miss it with STPA as you would with PHA. It is interesting though, because they did that in that work. They did really replace STPA largely with PHA. Okay, the method it can be done. It can be done, even though it uses one guide word. As I mentioned, control. One parameter, control, two guide words. And you can force it. I wouldn't recommend it. The thing is, what happened was in the PHA, it was a loss of seal gas flow to a compressor. The seal failed without that barrier fluid. They had a leak, and they had an unwanted event with fire/explosion. And so the problem was the line was on the P&ID, but they didn't HAZOP that line. It was completely ignored. So they didn't do no low flow on that line. And the flow got blocked way upstream. It was a shutdown valve that closed, and it shut down and safely moved the process vessels to a safe state. But what they didn't consider, then they lost flow to that compressor seal, and it leaked. Well, you don't have to follow that chain of events all the way back to the shutdown valve. You just simply ask, what if we have no flow in this line to the compressor seal, and that would have taken care of it, and they would have caught it in the HAZOP. So really, it was some hindsight bias happening there, and it's the quality, the competence of the team, the thoroughness of how you look at things. You could just as easily have missed that with STPA if you completely ignored the line. It would have happened. What was the next question from B? What was the name of the drift PHA you mentioned? This was Delta PHA is the name of the method. And interestingly enough, this is a derivative from Rasmussen's migration toward the boundary model as well, which if you remember, pushing the margin to the boundary, that is drift. And so this is just another example where Rasmussen's work. Jens Rasmussen passed a few years ago, but he is so foundational to safety science and is used in so many areas. And this is just another one. This Delta PHA is a result of that same model, just as it influenced Professor Leveson's stamp model in the same way. Now, the Delta PHA was good, I thought. It is extra work. I mean, you have to identify potential areas where you may have drift. The word that was escaping me was normalization of deviance. So you start to deviate from a design basis, from a place that you've assumed you're always going to be at, and you start to drift from that, deviate from that, and that's you've all heard of normalization of deviance. This is a method to try to help HAZOP and find those things. And you can imagine how the amount of setup and preparation, I think, would be needed to bring into the team. So but yeah, it is a way to get at that. It's called Delta PHA. The other question, okay, I saw Jonathan put in the link. Thank you, Jonathan. The other question here, when I was talking about confirmation bias, I mentioned fixation. I didn't play that thought out with fixation. Confirmation bias, the word bias comes from the Kahneman and Tversky heuristics and biases cognitive psychology school. So they view heuristics as leading to potential biases and negative things, which is not untrue. You can definitely go that way. Gary Klein and his cognitive psychological school use these heuristics in kind of a different way, and noting that they're very useful. Okay, and they're beneficial, and Kahneman doesn't deny that and does agree with that, but he works more on the bias side and the negative effects of those heuristics. So anyway, the two got together and they did some work, had some understanding, which was good. But so the problem may not be so much confirmation bias when, let's say, an operator is troubleshooting something, diagnosing an abnormal situation. It could be more fixation, where they get new information and they're confirming a belief, and maybe they're getting evidence that's contrary to that belief and not changing, and they stay fixated too long on that belief or that theory of what may be wrong. That's the fixation part, is not changing your mind when you should. And so that's what I meant to say about that. Now, if you start with a correct set of beliefs, correct being safe, quote unquote, staying fixated too long on that may be okay. That may be one way to help that. I Sunday would like to see procedures mentioned where applicable. What should the operator be believing about a certain situation? That could be easily incorporated about procedures. I think that is something that would be very useful to try to define up front and help the operators in their troubleshooting about the known hazards and the things we've identified that could go wrong. So anyway, that is that question. Okay, well, I do appreciate everybody hanging on, and for you guys that are in the middle of your working day, have a safe rest of the day, and we will talk to you guys later. Take care.